In many real-world data sets, the variables which you measure or have direct access to, the observed variables, they depend on unobserved or latent variables. And it's the latent variables that sort of affect or produce the observed variables which you end up having access to. So to give some examples of this, I've listed some applications where this sort of structure appears. So the first one shown on the left-hand side here of the slide is automatic speech recognition. So in automatic speech recognition, the underlying latent variables are things like the sequences of words or phonemes that the speaker is uttering. And what you actually get to measure is the sound pressure waveform or features derived from it from the speaker. And in the task, what you'd actually like to do is work backwards from the sound pressure waveform often to figure out what the sequence of phonemes or words is that's being articulated by the speaker. In computer vision, a similar structure arises. The latent quantities are things like the objects that are present in the scene, their poses, and the lighting conditions. But what you actually observed are RGB, say, pixel values from a CCD camera. You don't have direct access, obviously, to the objects, but you might want to, of course, infer them or estimate their pose from data. In natural language processing, we often have documents that we're interested to process, and what we might be trying to estimate from those documents is the topic at any one position in that document. The topics dynamically change through the document in some systematic way, but you observe sort of words that are produced from those topics. There's another example I could have listed here from robotics, say, along similar lines. In robotics, we often have direct access to the position of the object of the robot, and potentially, joint angles if the robot has, say, articulated arms. And what we get to observe are noisy sensor values for those variables, things like the position and how bent the object's arm, the robot's arms are. So it turns out that Markov models are going to be inappropriate for modeling this sort of data. Not only do they not have any notion of latent variable or notion of how the latent variable could affect the observed variable, which might be useful to put into a probabilistic model, even if we're interested in modeling the raw time series, the sequence data, the observed variables. It'll turn out that the Markov models are limited and are not accurate for reasons that we'll come to in a minute. So the solution to these issues is to go to a more general model class called hidden Markov models. And that's what the next few lectures are going to be about. These are very widely used class of models, which is why we're going to consider them. And they have a really simple structure. So just as before, where I have been using the term Y or the symbol Y, that's going to stand for our observed quantities. So previously we were modeling Ys with Markov models. Now Ys are going to be our observed quantities, and we're going to model them in a slightly different way. X is going to stand for our latent quantity. So the sort of the underlying or hidden variables, which we don't have direct access to. And we're going to simply put a Markov model now over these latent quantities. So this might be a first order Markov model, as in the case above here. It could be a second order or even higher order. Here it's a first order. So the latent variables are assumed to progress according to a latent Markov model. And then the observed data, the Ys shown here, are going to assume to be generated in the following way. They're assumed just to depend on the current state of the underlying latent variables and nothing else. So the arrows come just from the latent variable at that particular time instance, down to the observed variable below. So you can see that this probably makes sense for things like speech recognition. The word which is currently being uttered determines the current value of the waveform that's being observed. The current position of the objects in the scene and what objects are present determine the pixel intensities in an image, and the current positions of the joint angles and location of robot in the space control the value that the noisy sensor is going to measure. So that's why we're going to use this structure. And sort of formally, the joint distribution can be written down in this way here, where you have a Markov model over the x's again, and this instantaneous way of generating the observed variables y of t given x. And notice here, I've sort of used one piece of sort of shorthand notation. This time index starts at t is equal to 1, and you can see there is no initial state emission probability for the x's. And so the way that I have handled this is using the sort of shorthand that if I plug t is equal to 1 into this Markov model, I get p of x1 given x0. There is no x0 up here, and that's just going to be shorthand for distribution over the initial state, and it avoids us having to have a bit of bookkeeping to keep track of that initial state probability by using this sort of shorthand definition. So this will keep the equations compact in the following slides, if you're wondering where it's disappeared to. Okay, so I said a few minutes ago that modeling the observed data directly using a Markov model, it will be completely inappropriate in these tasks. So even if you didn't care about the latent variables and estimating latent variables, which of course you can't do using the Markov models we've been looking at before because they don't have a notion of latent variables, even if you just cared about modeling the sequence, using a Markov model would be inappropriate if you're in one of these situations where there's sort of underlying latent variables giving rise to your data. Why do I say that? Well, let's imagine marginalizing out our latents. So let's just compute the following integral over the joint distribution. Let's integrate out all of the unobserved stuff and look at what the distribution over the observed sequence is. When you do that, it turns out that you obliterate all of the conditional independence relationships from the Markov model. So I'm not going to prove this to you, but essentially the new set of conditional independence relationships that remain are essentially the most general setting. That is, there are arrows between every variable and every previous variable to that one. So y3 in this case ends up becoming connected to y2 and y1, even though the initial HMM from which it was derived from up here at the top, even though this had Markov structure in its latent variables. That Markov structure is destroyed when you marginalize. So the resulting distribution over the data is not Markov anymore. There's no Markov assumption buried in there. And so if you do have data which comes from an HMM, you can't accurately model it using a Markov model of some finite order. Good. Okay, so that's some basic properties of these models and just talking through their model structure. What I'm going to do over the next two video chunks is talk through a couple of prevalent examples of HMMs. There are lots of examples of these sorts of models, but we're going to look at two of the most simple and basic variants. And the first one is going to look at the case where the latent variables are discrete. You could think about this as being relevant for the automatic speech recognition example, where we have a finite number of words present at any time point. So we're going to look at discrete settings of the latent variable first. And for historical reasons, this type of hidden Markov model has been called hidden Markov models. So often when people say HMMs, they are restricted to thinking about discrete X. But here we're taking the more general perspective that this applies to discrete X and indeed continuous X. And so in our second type of hidden Markov model we're going to look at, that's called linear Gaussian state space models. This again is from more of the control and signal processing community. There we're going to have continuous valued latent variables. This might be really appropriate for our robotics example, where the underlying latent variables are things like position, velocity or joint angles. So they're going to be real valued quantities, and the observed variables in this case are going to be real valued quantities as well. So that's what we'll be covering in the next two video chunks.